to ask you if you can turn on your camera just to see your face at least once. Okay. So good morning. So just two. Okay.
Good morning.
I see myself, it's very small down there. Okay, much better now. So, okay. So more or less all of you. So welcome to this course, and I know the situation is difficult. I think all of you are here in Trieste, more or less, but well, because of the government rules, we are not allowed to. Oh, I'm alone, so I can remove my mask. So we are not allowed to meet in person. I hope the situation will change, but I'm pretty sure it will not. So probably we are going on all the course in this way. And so the course is a course in functional analysis, and basically is linear functional analysis. So these are pretty classical arguments, and well, I'm sorry for you, this will be the course that I followed when I was young. And so I don't know how many of you have already done some arguments, so let's see, just to begin with, how many of you knows Hahn-Banach theorem? Okay, so it seems no one knows Hahn-Banach theorem. I'm very happy, so today will not be boring. And the book that I'm following is the Heimbreit-Zies functional analysis, which has also exercises, and the tutor will do some exercises on the subject. So let me say that this thing, maybe it seems not difficult, but are really the basic tools in functional analysis, even the nonlinear one. So I hope you enjoy it. And another thing I want to say is, in my institute, as a non-written rule, we do the course divided in two parts of 45 minutes each, simply because it is required not to be too much tired in front of the screen. So while in person we can give a lecture of 1 hour and a half, in remote teaching, they suggest not to have more than 45 minutes in front of the screen. So I asked, and this is allowed here. For me, there is no difference since I will teach on the blackboard, and I'm asking you if you prefer 1 hour and a half in one slot, or just the Italian way or the SISA way to divide into 2 slots. And actually, please answer, because it's very difficult to talk in front of the screen not having any feedback. So you can just tell me something.
For me, I think 1 hour and a half is better.
Okay. 1 hour and a half, then? The others, what do they think? It's only one vote so far out of 6.
I agree with Yunus. I'm also fine with 1 hour.
1 hour and a half. 2 out of 6.
One and a half hour is okay with me as well.
1 hour and a half also for you, 2? Okay. And the last one, I don't see the other 2, and then
I didn't try the other way, so I don't really know, but it doesn't matter. I think 1 hour and a half is fine with me too.
Okay. Okay, so
Excuse me, Professor, just a technical issue, Massimo from the control room. Could you please remove your mask because it's touching the microphone? Thank you very much.
okay. Now is it better?
Perfect.
Okay. Okay, so another thing is, please, since it is very difficult to interact now, because, well, I have to stop and look, and it's very uncomfortable to look at your face and to understand. Well, first, it is very uncomfortable because the position is either very high above the blackboard or in the side of the desk, so it's very uncomfortable. And moreover, it's very difficult to interpret what is your mental state, I mean, how much you understand of what I'm writing or doing. So it's very important that you interrupt me, because otherwise it's like teaching to an empty space. And this is not very rewarding, let me say, to say the least. Okay, so now we start, and you have, so the start is I will try to write, and then you have to say if you see what I'm writing and if you understand or not, okay? And then this is the first step, and then we will go on. Okay.
Professor, may I ask what is the name of the book again?
Of the book?
Yes, the author
is,
of the book.
Is functional analysis of high-resist. I mean, I write on the blackboard.
Okay, thank you.
Okay, so this is the title, and this is the author. There are several versions. I think the last one is also the exercise. The one that I have as the exercises, which is the best, because we will follow these exercises. Okay, so far so good. So we can start. And the thing we can do is the Hahn-Banach theorem. So this is the first subject. Gosh. So let me roughly say what does the Hahn-Banach theorem says. So roughly say roughly. Okay, it states that you have enough continuous linear functional over, let's say, topological linear space, but in our case, we are normed space. So what does it mean you have enough? You have enough to do the operation that you need to do. So another important remark is that, well, being a normed space infinite dimensional, you have not every any linear function is continuous. So that's a remark. The continuity is important here. Is non-trivial, let's say. Okay, and maybe during the tutoring you will see how to build non-continuous linear function. I don't know. It depends if you're interested or not. In any case, okay, you have infinite dimension. You can put whatever you want on, and growing factor along each direction. Okay, so this is the idea that we need to take into account. And now let's see how the proof that you have a lot of continuous linear functional works. So the first is really the theorem. Okay, and a remark, let me add something. So here we will consider mainly real vector spaces. Okay, you may wonder why. Maybe if in the tutorial I will ask how to show that these results can be extended easily to the complex case, and the fact is that the complex case can be interpreted as by doubling the dimension, no? So instead of having the product with complement, you consider the product in R2. So here we stay with real vector spaces. So the statement is the following. So let P is a function. So E into R with E is normand. Well, it is linear here. It doesn't matter. Linear space. Such that, okay, the properties are the P is positively homogeneous. And is subadditive. Okay, and the remark here is that this guy is similar to a norm, more or less. Now, we have now a subspace and a linear function on G. So linear means, well, essentially means these two quantities, but lambda can be in R, and here you have the equality. Such that G of X is less or equal than P of X for all X in E. Then exists F R linear extending G, which means that F, when restricted to the vector space G, is equal to G, such that F of X is less or equal than P of X. Okay. So it's a pretty general statement. And now let me stop and ask if you can read and if you have any questions about it. So how is the situation now?
Yes, we can see.
Is okay? Is it okay?
Yes.
Okay, by the way, everything is written in the book. So you take notes just to help reading the book. Okay, so let's do the proof and then some comments. So the idea is to, so we define, well, let's see what is the idea here. The idea is that, well, since this is just as a, so okay, let's do idea. Let's do that. Idea. Okay. G is contained in E. But okay, if G is equal to E, there is nothing to prove. And there exists, let's say, X0 not belonging to G. So I want to define let's say the extension of G, F in G, okay, in the linear span of G and X0, R, which extends G, it is linear, and, well, I need to require this control. This control is the continuity in some sense, no? So f of x, e of x. So this is the driving idea. So suppose I have a subspace. The subspace is not the whole space. So let's start by adding one dimension. Okay? Okay, so what, since it is an extension and linear, then what I do, I have that f of x plus t x0, so this is in G, is equal, so linear, it is f of x plus t f of x0. Because I'm using here that is linear, and is equal to G of x, because f restricted to G is equal to G, plus t f of x0. So essentially, so I'm saying if f is a linear extension, then this relation holds, and at the end I have only to ask this quantity here. So I need to find let's call it alpha, which is equal to f of x0, such that let's write g of x plus t alpha is less or equal than p x plus t x0 for all x in G. So essentially, this is the only part which is non-trivial so far. I can, because I can always add one dimension by choosing this value here, whatever I want. But I need to require the control on F, and the control translate into this relation. This holds for great T and T in R. Now, X is a linear space, sorry, G is a linear space, and my functional P is positively homogeneous. Okay, so, okay, the previous inequality translates into, okay, if t is greater or equal than 0, I can collect it on both sides and divide. Plus alpha this is for t greater than 0. T equal to 0 is automatically satisfied. For t less than 0, I have to collect minus t. So when I divide, I get And this is the one that I get for t less than 0. Okay, so alpha should be chosen both in, so it's alpha should be less or equal on the other hand, should be greater or equal than the okay, but the x, let's say x prime here, they are two independent quantities because alpha does not depend on x. Okay? The real value alpha exists if and only if, well, the supremum over x prime of the left-hand side is less or equal than the infimum over x of the right-hand side. Okay? So, and this happens only if, so this is equivalent to say that their difference is positive. So the difference between these quantities is P minus the difference, which is okay, and now I observe that this guy plus this guy minus so this is the last inequality, and now I'm using the subadditivity over here. Can you hear down? Okay, yes. So it is now P
H prime, not H.
pardon?
In this right-hand side, X prime minus H0. No, right-hand side. That's for P.
No, well,
P.
P. Yes. So this is the sum of the two objects is x plus x prime, and then this is greater or equal than 0 by the assumption of G. Okay. So this is essentially, let's say, the step add one dimension. To G. Okay? And so now we conclude, and it depends if you believe in the axiom of choice or not, the space where you can conclude it. So if we will assume the axiom of choice, if you don't believe in it, you can do that for a separable space. Otherwise, okay. Yeah. So let's now I will cancel this step because we know how to add one dimension to G. So this is, let's say, proved. And now we assume the axiom of choice and we conclude. Okay. So essentially, I know how to add one dimension to G. So let's define the family P, which are the function, which is, okay, how do I say this? Just not to confuse the notation. So are the family of linear functional which maps some linear subspace, the domain, into R with the properties, well, whatever the properties that I just proved. So what is this extension? So H is linear. H restricted to G. So let's say G is contained in the domain of H, the domain of H is equal to my original functional, and H extends, this is already written, and H of X is less or equal than P of X. Okay. So this is non-empty because we have at least G, and then I have a rule which tells me that if you give one of these H, you know how to build one which is a slightly larger domain. So now we order, so partial order is set as, okay, let's say, the point H, considering P, is below the set, the point H prime, if domain of H is contained in domain of H prime. So essentially, H prime is an extension. And H prime restricted to the domain of H is equal to H. Sorry, I'm burning. Okay? So this is the first thing. So the idea is the following. So roughly speaking, what we can build through this step is if I'm giving you one H in this family, I can find an extension. So I can build essentially a sequence uncountable, depending on the dimension, of extensions of G. Finally, I want to say that, well, there exists a maximum here. So the properties of P if Hi is a sequence, is an ordered, an ordered set, subfamily, subset of P. So ordered means that for all Hi prime, either, let's say, it holds H is before H prime or H prime H. So one of the two is the extension of the other. This is the property. So this is the assumption of the property. Then there exists a maximum element such that Hi so it is the maximum with respect to the whole family. So this part is a pretty theoretical part. So how to prove that this is the property? Well, trivially, so how you would define what is the supremum, the maximum?
For D of H, we get union of all D of Hi. Union of, yes.
And how to define H?
H is equal to,
Pardon? H?
H of X equal to HAX if X in the DHI.
So H restricted to DHI is equal to HI.
Yes, or in other words.
Yeah, this is an extension simply because big ordered, this value is independent on I. Okay? So now we conclude the following that, well, now we need to apply the lemma, which is a Zorn lemma. And here I'm not going to prove it because, okay, I don't believe in it, but it's too long to discuss this thing here. So there exists H bar, which is maximum in P, which means cannot be further, so the domain cannot be further enlarged. Okay. And now the last part is that, well, this H bar is the extension. Okay. You know why?
Otherwise, we can get another element doesn't belong to the, yes, we can.
Exactly, because this
one dimension.
This step, the first step tells me that if it is not the full E, I can enlarge it by one dimension. And this contradicts the maximality. Contradicting the maximality. Contradicting the maximality. And this concludes the proof. Okay, so now I want to know if you understand, you like this way of teaching, you have any questions, because this is basically the style of the course.
Yes, it's okay.
Okay?
Okay.
So, okay, now we start with the application. So let's keep this Anbanach over here. And we see immediately a lot of applications. Okay, the remark, as I said, is that if you don't believe into this Zorn lemma, then what you can do is that you can add this step countably many times. And so what you obtain is that, well, it's not that the dimension of the set is countable, but actually you obtain some relation on the topology. It cannot be so general. But it's slightly longer, the discussion, so this is a statement which is okay. So let's put it here, theorem of Anbanach. And okay, it's that, okay, let me let it here. So now, definition. So E be a normed space. So the norm is norm of x greater or equal than 0, norm of lambda x is equal lambda norm of x, and norm of x plus y less or equal norm of x plus norm of y, just to remember. So you see that the norm will play the role of this functional P. Okay? Okay, the space, the dual space, this is important. Let me change color. E star is the space of continuous linear functional f over E. Okay, linear functional means that, well, I don't know if this is an exercise with the norm. Norm of f on E star is the supremum over the vector with unit length of fx. And this is the notation for duality. So this is the notation. Well, sometimes you use this one or the other one, depending on what is easier for f applied to x. So this notation is because it recalls the scalar product in some sense. And indeed, when you have the Hilbert space, it's really the scalar product. Okay? So what I didn't say here is that having this norm finite is equivalent to the continuity. But maybe you will see in the, well, it's easy to prove, or you will see in the tutoring. Okay, and so some remark here. F continuous. F continuous means that, okay, it's continuous, the topology generated by the norm is equivalent to norm of F E star less than infinity, and actually an E star is complete. And the fact that E star is complete is just, so what does it mean? It means that if Fn is a Cauchy sequence in E star, then there exists F, which is the limit of Fn in E star. Okay, and this is an exercise. I will not do this. Well, if you try, it's easy. Okay, so corollary of Ann-Banach. First corollary. Let G E normed space and G continuous in the topology inherited from E. Okay? So this means that with this observation, it means that the supremum of Gx for x equal 1 and x belonging to E, to G, is okay, less or equal than, okay, some norm, which is, okay, let's call it the K Let's recall then K, doesn't matter. Or let's say, put the norm of G. E star. Okay? Then there exists F on the whole space, sorry, G in R, the whole space extending G, and such that the norm of F is equal to the norm of G. Okay? Which in finite dimensional space is very trivial, since you say that you take the orthogonal space and put F equal to 0. Or what, not only 0, but 0 is a choice. So the proof, okay, the proof I want to use the Han-Banach, and the Han-Banach requires that I need to have a functional P and I need to have the G P of X. Okay, so the only thing I need to do here is to specify what is my functional P. Okay, any suggestion?
Norm. Norm.
What, pardon?
Norm, norm.
I don't see. Pardon? Because you are over here, I'm sorry.
A norm in
The
space.
norm times by linearity Gx, Gx divided by norm of x for x different from 0. For 0 is trivial. And this is less or equal, doesn't matter which is the notation, is the norm of G in E star norm of x. Less or equal, sorry. Okay? So with this choice, I'm in the setting of the theorem because I have that G is linear on a subspace and I have a functional P which controls G. So the theorem tells me that there exists F on the whole E into R such that F restricted to my space G is equal to G, and F applied to X is less or equal than the functional, which is norm of G, norm of X. So the supremum, the norm of F is the supremum of this product, or this duality product, and less or equal, and actually is equal. Okay, so you see that immediately as an application, for example, you give me one, so this is the next application, sorry.
Professor,
Yep.
do you mean the norm on the dual of G? Like the norm of G is on the dual of E or of G?
Difficult to understand, I'm sorry. Pardon, you said?
norm of the functional G? Is it on the dual of E or the dual of G, the subspace?
Okay, here it's a little bit, well, you can, is in the dual of G or the dual of E is the same. Because I say that the norm.
Just because it's not defined on all of E or something.
Wait, I'm saying it's the following. Sorry, I need to stick this guy somewhere, somehow. Okay. No, he's not going to. Okay, if you define this like the supremum, okay, it's just a notation. This is just a notation. I'm not saying that it has any meaning. If you look at this guy, it's the definition. If you call this quantity norm of G is star, it's okay. This is just a notation. Don't get confused. So this is a notation to say what is this object here. I'm not saying it's a norm. But I'm saying that the supremum of F is equal to, the supremum of G is equal to the supremum of F. And then I say that the norm, if you prefer, you can add the norm of G star, if you want to stick with the definition of norm of the dual space.
It's about the inequality, because there was an inequality.
I say an inequality, but you can, no, the norm of G is equal and the norm of G star, it is just a notation. I'm not saying, so let's consider in the proof that this object is just, well, here to here is the definition, and this one is just a notation. It's just I don't want to confuse with another space.
Okay, thank you.
Yeah, it's just so corollary, another corollary, and then this tells you why I say that you have a lot of linear functional, is that corollary for all x0 belonging to E, there exists a functional f0 in the dual. So the linear function which is linear and continuous, such that okay, the norm of f of f0 is equal to the norm of x0, and well, it points in the direction of x0, which means the f0 applied to x0 is equal to x0 squared. Okay, and when I forget to write in which, with respect to the spaces, should be easy to see that this is being a dual, is the dual, and this is being the original, is the original, and this is the original. Okay? So you see that we have a lot of linear functions. Okay, so how to do that? Well, we are still in the same setting. So now we have to define essentially the functional P and the original linear functional G. P will be the norm because I want to control the norm, the continuity, and G will be the one-dimensional space R x0 maps to R defined by, okay, what I need to have, you see, f0 should be an extension of my G. So in particular, this is equal to G, should be equal to this guy. So G T x0 is equal to T squared. So this function automatically satisfies this part, and its extension will satisfy the same, being an extension. So now I have to check this part here, so I need to define the functional, and G of tx0 is clearly less or equal than, okay, being the norm that the norm of x0, the norm of tx0. So it's, and this function here is my p of tx0. Okay? Apply this tension, there exists f0 such that, okay, extending g, which means that f of tx0 is equal to t norm of x0 squared, and such that f of x is less or equal than, okay, was it this norm? Yes, is a norm of x0 norm of x. Because my functional is norm of x0 norm of x. And this gives that the norm of f in the dual is less or equal than the norm of x0 in the original, because it's the supremum. So this is equal to the supremum with norm of x equal to 1 fx, and then observe less than x0. On the other hand, I have that f applied to x0 divided by norm of x0 is equal to, well, let's compute it from here, norm of x0. So the supremum is actually a maximum, and is exactly norm of x in x0. Okay? So far, so good. And now we reach the first stop. Okay, so the function, we will not use the duality, which the duality map is not here, doesn't matter. So, and the last important corollary, which is very important, for all x in E, the norm of x is equal to the max norm of f equal to 1 fx. So the difference between this statement and this definition here, well, this is a definition, so I don't have to prove anything. This is a statement. I have to prove that this holds. Okay, so proof. Well, first of all, well, I get that this object, by definition of the norm, is less or equal than norm of f, norm of x, by definition of norm in the dual space. Okay? And then I get from this fact that the supremum, I don't know if it exists, of fx when the norm of f is less or equal than 1, okay, is less or equal than the norm of x. But then now we have this corollary, which tells me that there exists at least one vector. There may be more than one, because what I'm applying is well, the axiom of choice, so you can choose another extension. So there exists an f such that this holds. On the other hand, if f bar is okay, the linear functional of previous lemma, then f bar divided by norm of x does the job. Okay, so let me discuss, is just to say if I divide f bar divided by norm of x, from this observation I get that it has norm 1, and from this observation I get that f along x is equal to norm of x. Okay, so I'm dividing essentially both qualities by norm of x. Okay? So this is the first point. So questions here? Otherwise, I don't know, observations, whatever you like. You want me to move another side of the blackboard? It's pretty generic. The theory is very generic, and the important thing in this part is to remember that you have a lot of linear functionals, and they are able to measure or to distinguish a lot of things. So far what I'm saying is that they're going to measure a lot of things, and here I'm explicitly showing that they measure the norm. The second part is how to interpret this Hahn-Banach theorem in a geometrical way. Okay, so if you're okay, we can start with the geometrical interpretation, which is as important as the two corollaries I just stated. So the extension of a linear functional and the existence of a particular linear functional for every direction. Okay, we can go on.
Yes.
Pardon? Yes? What's yes? Because it's difficult really to. Okay, I get it as a yes. So geometric form of Hahn-Banach. Here we cancel. Okay, so again, what roughly speaking I'm going to state here. So roughly speaking, since my idea is that I have a lot of linear functionals, roughly speaking, I'm saying that so roughly, let's say, I have two convex sets. And then I have an hyperplane separating them. However, we must be careful because we are not in finite dimensional space. And so we have to specify what is a hyperplane for us and if you need some property here. So let's be more precise. In finite dimension, it's just a drawing. But in infinite dimension, at least locally. But in infinite dimension, even locally, you don't have compactness, and then you have to be careful. So what is a hyperplane? If H is equal to f to the minus 1 of alpha, where f from E to R is linear. So I'm not requiring it to be continuous. Indeed, this is a statement. H is closed if and only if f is continuous. Okay, let's say that f is linear and non-zero. Okay, because if it is 0, it's the whole space, and alpha for alpha equal to 0. So the proposition tells you that the closure, as in the drawing here, the closure of this line is equivalent to say that essentially here the normal to this space would be the f. It's the scalar product x times the norm. So proof. So one part is very easy. Okay. So one part is very easy, is that f is continuous. Then H is closed. And this is by definition of continuity, being the inverse of a closed set. On the other hand, if H is closed, okay, so let's make the drawing. So if H is closed, I take any point, let's say x0, and I have a ball which does not intersect f equal to alpha. Since x0, let's say a ball centered in x0 with radius r, not intersecting. Okay, in, let's say, f to the minus 1, r minus alpha. Okay? So the correct notation here should be like this one. Okay, and then let's see if you think it's trivial or not. Then f, let's say if f of x0 is less than alpha, f of the ball is contained in, okay, let's say the values are less in the interval minus infinity alpha. Is that trivial for you or not? Okay, let's see why. Because if f x0 plus rz, or let's say plus z, or well, let me say, because let's say f of the ball is convex set. Being a linear function, the image of a convex set is a convex set, and now we are in R, and so it cannot cross alpha because it's a convex set not containing alpha, because by assumption I say that this ball does not, its image does not contain alpha. Okay? Okay, the other case when it's positive, doesn't matter. In particular, okay, now I'm saying by linearity. F of x0 plus r f of z less than alpha for all z equal to 1. Or less than 1, doesn't matter. Well, if I close it, I get this. And I close it not by continuity, I close it by linearity. Okay? And then this means what? F of z for all z with norm of z less or equal than 1, f of z is less or equal than, okay, alpha minus f of x0 divided by r. Okay, so the supremum is less or equal than this quantity. Okay. So I discovered this important thing is that the closure of an hyperplane is equal to the continuity of F. Now, I come back here. So now it's clear more or less what are the hyperplanes I'm going to consider. Are hyperplanes which are closed, which corresponds to level set of continuous linear function. So now I want to specify what does it mean to separate two sets. So H, the hyperplane H, separates A, B, contained in if there exists alpha is, okay, if, let's say, alpha is fixed here, f of A is less or equal than alpha, and f of B is greater or equal than alpha. Okay, so it means that they can touch on the hyperplane, but one stays on the part above and one on the part below, on the level set below. Then H separates strictly A, B, if now, so the separation is now uniform. So there exists epsilon greater than 0 and the same hold. F of A less than alpha minus epsilon, and f of B alpha plus epsilon. So now the difference is that I'm saying that there exists some space here. So this is the strict separation, and the other is that, okay, it's just a separation. Okay, and now the important thing about the Hahn-Banach theorem, which tells me I have a lot of linear functional, which means I have a lot of closed hyperplanes, is that if the two sets are convex and at least one is open, then there exists a closed subset separating them. So let's see that theorem. Which is Hahn-Banach. The first geometric form. Let A be convex. Okay, non-empty, just otherwise it's trivial. And disjoint. And, okay, I need an assumption, which is A open. Because the continuity needs, well, we will see. Then there exists H closed hyperplane separating them. So they are separating in the weak sense. Actually, okay, once being open and the other being continuous means that one of the inequality will be strict. Okay? Okay, so to do that, we do a piece, which is another object. So, okay, I don't know how to say why it is natural. At the end, when you see it, it becomes natural, but it takes, it's difficult from here, starting from this statement to arrive to the first step. So let me now do what you need, and then you will see why it is needed. Definition. So suppose that C is a set, open and convex, and the 0 belongs to C, then define the gauge of C as P of X is equal to the infimum of lambda, such that lambda real, such that X over lambda belongs to C. And okay, let me say what is this object. This object is, well, maybe with an example is clear. For example, if you take the ball of radius 1, the gauge of the ball is equal to what?
The norm.
Norm of X.
Is the norm. So essentially, this gauge is something which will be equivalent to the norm because it is open, and hence, okay, it contains a small ball, and it takes also into account the geometry because it's not, well, it satisfies the assumption, the Hahn-Banach theorem, without only for positive lambda. So it's something like a deformed norm, and this is what will play the game into the Hahn-Banach theorem. Okay, so let's see the properties, and maybe it's lemma. It holds. It is okay. P is subadditive. P is positively homogeneous. P is bounded by the norm. For some M. And the set C is equal, the set C, the one that I used to make the gauge, is equal exactly to the X such that P of X is less than 1. Okay. Now the proof is, well, is not difficult. It's just, the first one is just stupidly technical because you have to. So I will not do that. I will just try to do a sketch. Because it's a nice exercise. So the first one is trivial. Is that true? Do you agree on the triviality of the first one, the second one? But it's just by the definition.
Yes,
If you
yes.
multiply by alpha here, then you multiply by alpha here, then you get alpha here, and then you plug out the alpha. So the second, let's call this A, B, C, D. So B is trivial. And now A. Why is A so? Because C is convex. Okay? So I just do a drawing. hoping that you understand. So I have C here. I have the 2 points. I take the middle point, because I already know that it is positively homogeneous. Then I have to divide by this point. I have to divide by that point. And then the projection of this guy, okay, this is convex. Let me make a little bit. So if I project along the linear line, the linear segment between the two projections, then I get something which is a lambda, which is larger than the actually needed. And if you do the computation, you obtain that in order to project this point here, you need exactly p dx per piece y divided by 2, because I'm in 1/2. Okay, so this is the exercise. What about C?
Implied by the C is open set. So
Yes, because it contains a small ball.
yes.
Let's say B of 0, 1 over m is contained in C. And so if you divide by 1 over, if you divide by m times the norm, you get something which is inside C, because it's inside the ball. So what about D?
By the convexity of C, it implies.
Well, not by the convexity, by the fact that this is, well, it has the convexity with 0, is the star shape. But yes, it is the convexity. So essentially, if you take a point, then you can enlarge a little bit and you're still inside C. Okay? So let's say star-shaped. Okay, so these are the properties, and essentially you see what I need is that, so let's use what I need here. Well, this is exactly the Hahn-Banach statement, and this guy will tell me that I get something which is continuous. Okay? Otherwise, I get something which satisfies the inequality with some p, but p would not be the norm. But with point C, I get the norm. Okay, so I think I have time exactly to prove the geometric part, and then we are done for today. Okay, so again, I need a lemma. Or is a particular case of the theorem. Lemma. So C is contained in E convex, open convex, and 0 belongs to, wait a minute. I forgot one assumption here. 0 belongs to C, and x0 does not belong to C. Then there exists H closed hyperplane separating C and x0. Okay? So let's make the drawing and then you will see. So the drawing, I have 0 here, this is C, and then I have point x0. So I need to define a functional which uses, okay, which separates at least the C from x0 in a subspace, and the separation is encoded into this fact. So the functional should be 1 over x0 in order to have a less or equal than P of X. So let me rewrite things. I need G, and this is defined, okay, on the easiest space, which is this one. Such that G x0 is equal to 1, so this is linear, then it is defined, and G of T x0 less or equal than, well, or this is greater or equal than 1, doesn't matter, less or equal than P of T x0. Because this would encode my property, no? So, and then the extension F will do the job. Okay, but now what I have now, well, this is basically trivial because the function, so define G of x0 equal to P x0, and then it's okay. So I have a function f of C is less or equal than P over C, and this is less or equal than 1, but f of x0 is equal to G x0, which is equal to P x0, which since does not belong to C, this is less or equal, okay, this is less than 1, less or equal, greater or equal than 1. So the hyperplane is H equal, so the hyperplane H is F equal to 1. Okay, now we have everything, and the proof is very easy at this point. So with these two, this lemma and these two lemmata, now we prove this proposition, this statement. So define proof of theorem. A minus B. This is convex, open, because A is open, and 0 does not belong to C, because they are disjoint. So open is A open, and 0 A intersection B is empty. Okay? So now the previous lemma tells me that I can separate a point which has 0 inside from a point which is not inside by translation. So by translation, and the previous lemma, there exists H closed hyperplane separating 0 from C. Okay, I just translate everything in order to have a point 0 inside the set C. And then if you go back, all the relations are linear. I'm just changing, instead of having f equal to 1, I will have f equal to 1 minus f of x0, for example. Okay. So H. So this means that 0, which is equal to f of f0, is, okay, let me say, if I say less or equal, is greater than f of c, f of x minus y for all x in A, for all y in B, which is f of c. Okay? But now this means that f of y, x, is less than f of y for all x, y, x in A and y in B. Then there exists alpha. So alpha is greater than the supremum over A of f of x and less or equal than the infimum over B of f of y. No, because the y and x are independent. Hence, conclusion, f equal to alpha separates A and B. Okay, and this is the conclusion of the first geometric form. Okay, it's I stop here. There is no time to address the second form. Well, perhaps there exists time. Yes, I think we have time, so let's do that. So let me write here the second form. Banach. Second geometric form. And so here the assumptions are more or less the same, but are slightly stricter. So A, B contained in E, convex, non-empty, disjoint. Now A closed and B compact. Then there exists H closed hyperplane such that, okay, H separates strictly now A and B. Now, so I would like to discuss slightly before doing the proof, but the time is a little bit running, so let me do the proof, and then maybe during the proof I will discuss. Okay, so let's cancel this part here. Still proof of the theorem. So the discussion is why the compactness plays a role and the closure. The closure and the compact plays a role because it means the two sets are separated by a positive distance. No? So the one is compact, one is closed. It means that the separation is a positive distance. While here, okay, they are disjoint, but the distance can be equal to 0. And then still you can separate. So set, again, A minus B. Now, with the property is still convex. And now, since B is compact and A is closed, if you want to do by exercise, is fundamental that B is compact. and 0 does not belong to C. Okay, since it is closed, then there exists a ball around 0 not disjoint from C, because the complement of C is open. No? Closed. Okay, and now I can apply the previous theorem. So I have an open set, a convex set, another convex set which are disjoint. So I can apply the first geometric form to C and the ball, which is open. I need to check the assumptions. The assumptions are everything is okay, but the open, but okay, it's open here. So I'm happy. So there exists F of the ball is less than, and exists alpha less than alpha, less or equal than, okay, the F of C okay. So this means that alpha, I discovered the following, is that okay, here I write like or I write the opposite side. So I get that F of X. So this object here means that alpha is greater or equal than, let me see how do I do that. So what this means, alpha is greater or equal than 0 because is greater or equal than, if you take the supremum over Z, this is the norm of F times R. Okay? And from both, what I get that F of Y minus plus alpha 2 is less or equal than F of X minus alpha 2. Because being larger than alpha means that if I add alpha high Y on, so I bring F of Y on the other side, this is split by 2, and I get this object. So it means that setting epsilon equal to alpha Y, which is this value here, F of X is okay, less or equal than okay, here I didn't say what is the hyperplane. So there exists an hyperplane. Okay, then this means that there exists an hyperplane which is I forgot to say that you need to take an hyperplane H equal to F equal to kappa, separating A, B, no? But on the other hand, I have that F of X is less or equal than, from this guy, K minus epsilon, and F of Y from the other side is greater or equal than K plus epsilon, where the K is the one chosen, the one that separates the two quantities. Okay, sorry, I was in a rush, and maybe we'll see later the conclusion. But the conclusion is that the separation being uniform, then the alpha in between is separated by at least this epsilon, whatever is the K. So the supremum of this guy is less or equal than some K minus epsilon, and the infimum is less than some K plus epsilon. Otherwise, the difference of the two cannot be epsilon, 2 epsilon. Okay, so I stop here, and if there are questions, comments, you prefer other ways, you prefer, I don't know. It's difficult. Every class in this situation is different.
Professor.
Yep.
How many chapters is covered in the textbook?
How many? Sorry.
Chapters.
Chapter. Okay. This depends on. And indeed, one question is. So. The hope is to arrive at least to chapter 6, which is the basic course on functional analysis that you get in the Italian system. Master class you get is the first 6 chapters, more or less. If we want to be very optimistic, we could cover also some Sobolev, but it's very, very difficult. But certainly the compact operator is something which cannot be avoided. And on the other hand, it's already a lot. But I've seen, I have a question for you. What about the LP spaces? Which I've seen that has been covered in the real analysis course, at least partially.
Yes, of course, it's covered in real analysis we studied.
Okay, but the LP spaces, so the one, for example, the Kolmogorov theorem. Just a question.
LP.
The continuity of translation in LP?
No.
Yeah, because the difficulty is exactly that one. That okay, so I can skip LP spaces because it is a fundamental example, and then we go immediately to Hilbert and the compact operators. I will do that, and then in cases we will come back. So essentially, it will be chapter 1, 2, 3. Maybe I will add the Krein-Minman theorem, and 5, 6, and let's see what we get at that point. Okay?
Okay.
So have a good day, and see you more or less tomorrow.
Thank you.
Thank you, Professor.